Welcome to this explainer. We're diving deep into the actual mechanics of building truly persistent AI agents. Have you ever spent, I don't know, a whole hour teaching an AI the exact constraints of your project, only to have it completely forget everything the very next day? Yeah, it's incredibly frustrating. If you've been working with large language models, you know that creating an agent that actually learns and adapts over time is notoriously difficult. So today, we're breaking down a really fascinating technical white paper from the MindStone project. It introduces a concept called resonance-weighted recall. And look, this isn't just about making AI store random facts. It's about fundamentally changing how an AI collaborator weighs its past experiences to shape what it does next. Okay, let's frame the core failure of modern AI right out of the gate. Remembering facts is simply not the same as accumulating experience. Think about it. Current memory systems for LLMs mostly rely on simple retrieval. They store past information, find the most relevant records, and then just shove them into the context window. But the source material perfectly highlights a vital truth here. A library with a perfect search engine is still just a library. You can have flawless vector search, sure, but that alone does not produce a collaborator with accumulated judgment. So we really have to ask ourselves, why does standard AI memory fail so hard for long-running persistent agents? Why can an AI flawlessly retrieve a massive document, but completely forget a vital project constraint we literally just discussed yesterday? Well, the deep failure here is that standard systems do not accumulate experience in a form that reliably shapes future behavior. Think of a software engineering agent. It should get sharper at a specific codebase because it has actually lived through prior debugging sessions, mistakes, and trade-offs. But instead, what usually happens is that old, crucial facts just disappear as the context window fills up. It's kind of like a workbench getting so utterly cluttered that your older foundational notes just fall right off the edge. Or worse, the system surfaces technically related but operationally useless information. Section 1. The AI memory problem and why standard vector search falls short. This brilliantly illustrates the massive paradigm shift we're talking about, moving from purely semantic similarity to deep operational relevance. Standard retrieval basically just takes the current prompt and asks, what stored text looks like this? But a persistent agent actually needs to know what matters right now. A user correction from a month ago might be vastly more important to your current task than a semantically closer but totally trivial note from yesterday. Resonance-weighted recall, or RWR, doesn't just ask what text looks similar. It asks what prior experience fits the current task, the role, the source, context, and the risk boundary. Section 2. Layered continuity context. Let's zoom out to the macro view for a second. Persistent continuity actually requires all of these layers working together. But today, we're zooming in specifically on layer 4, indexed, source-aware recall. The layered continuity architecture tells us that memory isn't just a monolithic thing. You have your identity scaffolding, you've got the authoritative append-only transcript history, and you have curated structured memory. Resonance-weighted recall sits right there at step 4, acting as the ultimate bridge. It searches these durable sources and selectively injects only the highest value experiences into the live context window, and it does this before the model even generates a response. Section 3. The resonance scoring formula. We're deconstructing S plus E plus T plus A plus Q minus K. So we always start with semantic similarity, or S, as our baseline. But in this architecture, you've got to remember it's just a provider score, not the final answer. This is your standard vector search, finding paraphrases and conceptual matches. It's usually computed with embeddings and cosine similarity, which, simply put, is just mapping words to numbers to see how closely related they are. It's an incredibly useful starting net to catch relevant memories. But again, similarity is not authority, and it is absolutely not judgment. So we take this baseline S score and we start modulating it. Next up is the experiential weight, or E. This ensures that a past mistake actually changes future agent behavior. This is how the system truly learns. If an agent is explicitly corrected by a user, or if recalling a specific memory successfully prevented a mistake in a past session, that memory gains experiential weight. It means a highly critical safety rule or a reoccurring project constraint gets boosted right to the top of the pile. This ensures the agent doesn't just blindly repeat the exact same errors over and over. Then we add temporal salience, or T. This means a critical design decision from a month ago won't be totally erased by trivial banter from yesterday. Recency absolutely matters in an active task, of course, but different memory types need to decay differently. Think of it kind of like a half-life. A daily task note might have a half-life of just a few hours, but a foundational architectural rule for a coding project, that needs to be almost evergreen. Temporal salience applies a decaying boost, but it works in tandem with that experiential weight we just talked about, so the truly important stuff survives the test of time. This brings us to A for source authority. When the system pulls two memories that semantically match, it really needs to know which one to actually trust. Curated, structured memory, like an approved project decision, has the absolute highest authority. The raw transcript is medium authority. It's the ultimate historical record when exact wording matters. And way at the bottom, summaries. They're low authority because they are inherently lossy, meaning they shed important details just to save space and may totally lack narrative texture. Finally, for the additive variables, we factor in task relevance, or Q. This is huge because a software engineering persona needs entirely different memories than an incident response persona. Even if the user prompt uses the exact same words, the context of the task completely shifts what past experience is actually valuable. The ranker looks at the active role, the current project path, or even the specific Slack channel the agent happens to be operating in, and it dynamically adjusts the relevance score accordingly. Section 4, managing the token budget and the concept of ephemeral context injection. How do we fit all this in? Well, the system calculates this recall pre-inference. It brings relevant past experience into the working set as a temporary thought, not a permanent prompt addition. This is a massive, massive distinction. We are not permanently appending every single recalled memory to the agent's standing context. Doing that would cause immediate and catastrophic token bloat. Instead, the agent receives this recalled material as an ephemeral context block. It's injected right before the model begins inference. The past shapes the very next response, and then on the next turn, the recall is recomputed completely from scratch. To protect our strict token budget, the system literally ruthlessly deduplicates, because token space is expensive, right? And we absolutely do not want to waste it mansplaining to the AI something it's actually already looking at. If a critical safety rule is already sitting right there in the live prompt, the recall ranker detects that and just rejects it from the recall list. It also drops highly similar chunks. This strict discipline ensures that the tiny token budget we allocate for memory is only used to bring in high-value, totally novel context that the agent doesn't currently have in its active working window. Section 5, Safety and Privacy Guardrails. Let's look at enforcing the risk penalty. We have to ask the scary question. What actually happens when an agent remembers a private secret in a public chat? This is the absolute nightmare scenario for persistent AI, and it's exactly what the -k variable in our scoring formula is designed to prevent. Imagine you have an agent that works with you on a private, confidential repository, but it's also accessible in a public shared Slack channel. If someone asks a question in the public channel, standard vector search might just happily pull up your private credentials or sensitive internal context, purely because it was semantically similar. No way we can let that happen. That is where the risk penalty comes in. It rigorously demotes or completely filters candidates, keeping recall from becoming this indiscriminate and dangerous prompt stuffing. The system actively applies channel and policy awareness. If a memory is tagged as private, the risk penalty heavily penalizes or hard filters it the second the active surface is a shared channel. It also suppresses memories that have been explicitly superseded by newer facts, like an old password or a deprecated API key, or any memories that fall outside the active role's permitted scope. Let's dive into this core philosophy for a second. A safe recall pipeline is completely channel and policy aware. This really summarizes the entire safety model. An agent that simply surfaces whatever is most technically relevant without actually understanding the operational and social risks of the environment it's speaking in is frankly dangerous. Resonance-weighted recall inherently builds appropriate use right into the mathematical ranking of the memory itself. Conclusion: history versus working set. Let's wrap this all up. Always remember this fundamental rule. We never destroy the authoritative history. We simply use smart recall to dynamically curate the live working prompt. The live context window is just a bounded workspace. We prune it constantly using sliding windows to manage token pressure. But because we have the raw transcript saved safely outside the prompt, and because we have resonance-weighted recall dynamically pulling the most experientially, temporally, and task-relevant pieces back into the working set exactly as needed, we never actually lose the plot. We maintain a truly persistent, ongoing collaboration. So as we look to the future of AI, consider how experiential memory might actually finally solve the massive hallucination and over-compliance problems we face today. The source research notes that an agent with durable memory, one that actually remembers the sting of a user correction, becomes significantly less likely to confidently hallucinate, By weighting recall based on experience, authority, and task relevance, we're moving away from a flat search engine and stepping toward a system that genuinely learns the texture of its work. Thank you so much for joining me on this explainer. I really hope this gives you a new, inspiring framework for building the next generation of persistent AI.